Hi all. In this lecture, I am going to discuss the various characteristics of the energy eigenfunctions of infinite square wave. So what we have found earlier is the energy eigenfunction psi n of x for a particle which is confined in a one-dimension infinitely deep well is a square root of 2 by n sine of n pi x by L. So the situation is a particle is confined within a width L. So there is a very big wall at x equal to 0 and at x equal to L. So these are possible wave function. So what are the characteristics of this wave function? So the first characteristic is the wave function are alternatively odd and even function. So what is meant by that? Okay, so if you look at psi 1 of x, so if you put n equal to 1, you get psi 1 of x is equal to square root of 2 by L sine pi x by L. So we can just plot this. So if we plot this graph, GeoGebra. So here we are trying to plot the different energy eigenfunctions using GeoGebra. So what we are seeing is just the graph corresponding to the first energy eigenstate, the psi 1 of x. So we know that psi 1 of x is square root of 2 by L sine pi x by L. Okay, so here recall this capital L is the total width of the this one dimension box. This L we can fix from here. So this is a movable slider. At present this L is set to 4 and N I have put as 1, and this orange color shows that the value of the wave function corresponding to N equal to 1. So if you put N equal to 0, the wave function would be completely 0. You can see that. So n equal to 0 becomes the entire place the wave function is 0. That is not a valid solution. So the first non-zero wave function is for corresponding to n equal to 1. So psi 1 of this form. And here L is the width of this one-dimensional box, and the width of this one-dimensional box you can increase or decrease in this platform. Okay, so if L is like this, then the wave function would also change accordingly. And you can see that outside the this box, the wave function is always 0, it is not changing. And the shape of wave function is changing only inside this box. Okay, now for n equal to 1, we can see that the wave function is 0 at both the boundaries at x equal to 0 and x equal to n, and we are getting a maximum exactly at the middle of this box. Okay, so that we can understand if you put L equal to some integer. Okay, if you put L equal to 2, the total width is 2, and exactly at the middle L equal to 1, x equal to 1, you are getting the maxima for this wave function. Okay, now what would happen if if you're moving to the second state, psi 2? So for that you can put n equal to 2. If you put n equal to 2, the wave function takes this form. So it shows the exact opposite behavior of the first wave function. So remember this first wave function psi 1 is corresponding to the energy E1, which is the lowest possible energy, and psi 2 is corresponding to energy E2, so which is of higher energy. And so this E2, we can say that it is the first exit state, and E1 can be called as a ground state. and E2 is the first excited state. So when you're moving from the ground state to the first excited state, the behavior of wave function completely changes. So in the earlier case, we are getting the maxima wave function at x equal to 1 at exactly at the middle of the box. We are having the wave function maxima or probability is maxima. But for the first excited state, the wave function is 0 exactly at the middle point. So there is no probability to find the particle at the midpoint. So it is exactly opposite to what we have seen, the behavior what we have seen in the for the ground state. So the first excited and the ground state are showing exactly opposite behavior. Okay. Now the one additional point we can see here is in the previous case for n equal to 1. For n equal to 1, we are getting the wave function like this, and here the wave function is symmetric about x equal to 1 at the midpoint. Okay, so the wave function is very symmetric at x equal to 1, and if you go to x equal n equal to 2, then the wave function become anti-symmetric about the midpoint of the box. So the n equal to 1, we can say that the wave function is even function. So n equal to 1 is corresponding to an even function because about the midpoint it is symmetric, and n equal to 2 is an odd function. So it is exactly opposite. So the ground state wave function is an even function, and the first excited state wave function is an odd function. Now, similarly, if you go to n equal to 3, what would happen? N equal to 3, the wave function behavior is again changes. So we are getting maxima, so we are getting the negative maxima at x equal to 1, or the probability density maxima at x equal to 1. And the wave function becomes symmetric. So for the energy corresponding to E2, the second excited state, so that is also become an even function. And for n equal to 4, we will expect we will accept an odd function. Yeah, for n equal to 4, we are getting an odd function. So about the midpoint, it is showing exactly opposite. The psi of x and psi of minus x are different. Okay, so it is what is called an odd function. So when you change n, the value of n, the correspondingly wave function changes. So n equal to 1, we are getting a symmetric function, anti-symmetric, symmetric, anti-symmetric, symmetric, anti-symmetric, and so on. So whenever the value of n increases by 1, then the wave function changes from odd to even or from even to odd. Okay, so that is the one main point that we want to focus here. Now the another aspect is if you look at n equal to 1, if you look at n equal to 1 state, one wave function, there is no 0 in between. So between the edges, between the boundaries, there is no 0 point. But if you look at n equal to 2, we have one 0 point. So there is one point with wave function 0, or there is one point with probability density 0. And for n equal to 3, we are getting 2 points, and n equal to 4, we are getting 3 such points. You can see here for n equal to 4, we are getting 1, 2, 3 points are there. And n equal to 5, obviously, we'll get 4 points, 4 0 points between the boundaries. So the number of 0 points between the endpoints increases by 1 when in each excitation. Okay, so in the ground state, there is no 0 wave function point inside, and for the first excited state, when n becomes 2, we get 1 point. Okay, so for n equal to 2, we get 1 0 point, and for n equal to 3, we are getting 2 0 points, and so on. Now we can go back to our original discussion. So this is what we have discussed so far. So the wave function are alternatively the odd and even functions. So the psi 1, psi 2 of x, which is root 2 by L, sine 2 pi x by L. So this is an even function, this is an odd function. So the alternatively the psi n become the even and odd. So all psi 1, psi 3, psi 5, etc. are even function, and psi 2, psi 4, psi 6, all these are odd function. Okay. Now the second aspect is that is also we have discussed while discussing the illustrating in the GeoGebra. There is a number of 0 points. This is also called nodes. So number of nodes between the endpoints increases by 1 in each excitation. This also we have seen. So if the wave function and number of nodes in between, for psi 1 of x there is no node, and for psi 2 of x we have one node, and for psi 3 of x we have two node, and so on. For each excitation the number of nodes increases by 1. Okay, now the another important point is the wave function corresponding to the different eigenvalues are orthogonal. Okay, so more correctly we can state that the energy eigenfunction or the wave function corresponding to stationary state are orthogonal for different coordinates. It means if you integrate, okay, instead the orthogonality condition we have already discussed earlier. So the orthogonality means the psi m must be 0. That means integral minus infinity plus infinity psi n star of x psi m of x dx must be 0. So this we can check because we already know the expression for psi n is root 2 by L sine n by x by L. Similarly, the psi m, that would also be real root 2 by L sine, instead of n just use m, that's all. So this integration will become the integral inner product psi n psi m would be minus infinity plus infinity psi. Okay, so psi n psi m we can substitute, so it become 2 by L sine n by x by L and sine m by x by L into dx. Now we know that okay, there is we have to change the limit because the wave function is 0 uh, before x equal to 0 and it is 0 after x equal to L. So therefore this integration limit must change. So the integration limit must be from x equal to 0 to x equal to L. Now just perform this integration. So we have the product of two signs, and it is easy to calculate this integration. And if you do this integration, you can show that it is equal to 0 when n not equal to m. And you can also show that it would be equal to 1 when n equal to m. So actually this property we have already discussed while discussing the mathematical formulation of quantum mechanics. That is all the eigenfunction corresponding to Hermitian operator are orthogonal. So the same thing we are getting here. this all the psi n's. The psi n's are the wave function corresponding to stationary state, and they are the energy eigenstate. It is the eigenstate of Hamiltonian, and Hamiltonian is a Hermitian operator. So therefore, obviously, this all the psi n must be orthogonal. So the psi n corresponding to different energies must be orthogonal to each other. Okay, and moreover, since we are using the wave functions or the normalized wave functions, so the inner product of the wave function with itself should be one. So this condition we have already discussed earlier. The psi m inner product, it is delta m, or in the integral form we can write it is integral 0 to L 2 by n sine n pi x by L sine m pi x by L dx is Kronecker delta n. Okay, so this is again one important property of this energy eigenfunction. And last thing, which is we have already discussed earlier also, because all this psi n of x forms a complete set. Therefore, in general, any wave function of the system can be represented as a superposition of psi n of x, or more generally, the wave function psi of xt we can write sum over n cn psi n of x e raised to minus I e n t by h cross. So this is what is called the superposition principle, and superposition principle is used because psi n of x forms a complete set. Okay, so in the next class we will discuss how we can find the value for Cn, and we will also discuss what is the relevance of this Cn, what is the relevance of this expansion coefficient Cn. Okay, so for the time being we are going to stop it here, and we can just summarize it. So on summary, what we have found is we have just found out the characteristics or the properties of the wave function of the energy eigen functions of in case of infinite square well, and we found that the wave function are alternatively the odd and even function. So if psi1 is even function, then psi2 is odd, and vice versa. So on increasing of the value of n, the odd function changes to even function, and even function changes to odd function. And remember, this is not only applicable for infinite square well, it is applicable for all system with the potential symmetry. So that is the one point we have to highlight. Okay, so this property, this is valid for all v of x which is symmetric, or which is an even function. So if v of minus x is v of x, then this condition is valid. The wave function, the wave function, more correctly, the energy eigen wave function. Energy eigen wave function are alternately odd and even function. And second point, the number of nodes increases in each excitation. It is also valid for all potential. It is not only for symmetric potential, it is valid for all potentials. And third point would also valid for all potential, because there is a general statement, and fourth one is also for all potential. So except one, the other three behavior of the energy eigenstate is valid for the all potential. It is not only for infinite square well, even for all cases, all potential, it is applicable. Only the one condition is for the first one, it is the odd and even function interchange, the potential must be symmetric, the potential must be even function. That is the only addition point we have to remember, or otherwise the remaining things is applicable for all other potential. And this would be important while we are trying to solve certain numericals. So all these properties we have to remember as well. So thanks for watching this video. So we'll have the another session explaining how we can find Cn, and as well as what is the relevance of C. Okay, so thanks for watching this video.